Our first presenter today is Paul Pilarski. Paul is the regional bridge construction engineer for MnDOT, serving the North Metro region.
Yeah, I'm here to talk to you about a project I was involved in, investigating the effective repair of pre-stressed beam ends that were severely deteriorated. There'll be no torpedo grease in this presentation, as mentioned this morning. My presentation is going to first start out with how we repair concrete normally, our typical repair procedures in contract, and some of the concerns that we might have. And then I'll get into the backdrop for the beam research and the project that we repaired the beams under, and then subsequently we load tested those beams. How do we make these repairs? Usually we hand a contract to the contractor with some vague areas to be repaired, and the inspector for MnDOT would go out there and hammer sound the area of the substructure, identify what's good and what's bad, and hopefully there's more good than bad. And then the contractor chips off this delaminated concrete, searching for sound concrete. A lot of times what's causing all that spalling is corrosion of the rebar, and it's usually the most outward bar, the stirrups, which you're relying on for shear strength, and so you do have to replace corroded rebar, and it can be challenging when you got stirrups. A repair mix, a lot of times we're preferring to use Shotcrete, which is a dry cement, sand, and aggregate mixed and wetted at the nozzle and sprayed at high velocity. We find that to be the best repair for overhead and vertical. And to cure this, we're usually seeing a curing compound in a blanketed manner. And I mean by horizontally applied and then vertically to make sure there's no gaps. Now, if you look closely at these previous Shotcrete repairs where curing has not been optimal, you'd like to have a moist cure, but it's not always practical, you will see a network of cracks in there from shrinkage. And so when we started to see that in our repairs, we started to get concerned what's going on, and we started to ask more questions, especially if we're not relieving that structure or element of load during those repairs. So this is the bridge in question where this research all started, and it was a contract repair in 2013, and I'm just showing some before and after of those repairs. And so the questions we started asking is that Shotcrete a structural material? Is it helping us, or are we just covering up the deterioration? And how durable is it? I think a lot of people have the same questions. How long is this going to last? And then other questions. So first, let's talk about durability. Iowa has produced a nice report about what makes a durable patch, and the crux of it is that you must use a compatible patch material. There's other attributes like matching the elastic modulus, and you need a really good bond strength, thermally compatible, good compressive strength, and you must moist cure. Well, we usually don't get all those right. It's very hard to do a field installation that you're getting all those right, especially if you're limited for that time in the field. So we started looking at FRP as a new material to confine these repairs. We see a lot of research out there that shows that it will enable you up to 10 times the life expectancy for patch repairs, and it has some other benefits to it as well. And so to get familiar with FRP, we looked at a recent project where we did some column repairs. You can tell these columns were previously repaired, and we chose, this was by contract in 2015. A contractor chipped this away and shotcreted it and did it our typical way. And we chose this site for maintenance FRP application. We wanted to know as an owner, before we roll out FRP by contract, do we understand the material? Can we apply it? Do we understand the pitfalls with it? And so we chose this column. And some of the things in applying FRP, when we shot blast this, or sandblast it to prepare it for FRP, we noticed right away underneath all that curing compound was a whole network of shrinkage cracks that weren't observable before. And the shotcrete was really sound. It was tightly adhered, but we had this network of cracks. So it just led into additional questions about what are we getting for all these repairs. And in fact, if we're not load relieving, what's going on? Or is this patch participating, especially with the network of cracks? If you look at our ICRI, the International Concrete Repair Institute, they have a document about patches and what you might encounter if you remove deteriorated concrete and how the load may redistribute. And if it directly applies to that column, if you start looking at a strut and tie model, you're going to have a series of struts to redistribute those forces, and then of course there's going to be some tension in there also. And then you apply your patch, and if you want additional load to go through that patch, well, you may also develop some tensile stresses along the boundary of that patch. So we do see FRP as a good means to confine the patch, not only for preservation from new chlorides, but also for confinement of any section loss in those stirrups. So this was that particular column and where we FRP wrapped it, and that's where we discovered a lot of these shrinkage cracks underneath the curing compound from the start. So thinking about all these questions swirling around in your head, you might, when we start to think about pre-stressed beams, we know it can be a challenging problem. They're a lot of times directly under the joints, just like the piers, and so this repair project had a lot of these elements in it in 2011-12 when we scoped it. This was well before we discovered the Shotcrete issues, but we knew we had some concerns about Shotcrete, let alone the shrinkage cracks. So this bridge is located just southwest of Minneapolis. It spans over wetland, and it was built in 1974 by the county. It goes over poorly drained wetland and old roadbed. And it's composed of these AASHTO type 3 girders. They're 60-foot spans. There's 49 of these spans. And every other pier, every other piled bent has an expansion joint at it. Well, they had compression seals there at every other pier, and they leaked for many years until we assumed ownership when it became a trunk highway. We replaced it with strip seals, but largely the damage was done. So when we got into scoping, we saw a variety of deterioration levels with these beam ends, and we just went into contract with a Shotcrete style repair of patching. We also employed cathodic protection and passive thermal zinc spray on these beam ends. So here's a before and after as we got into contract. We had some minor small repairs, and you can see on the right the repair. Another one, you may have a little more exposure of the beam end and corrosion, and on the right, the finished repair. You can see the curing compound. And then we got into some larger beam repairs where more strand was exposed, in fact, the whole bottom row and some of the side. And I thought this was a large repair, but soon I learned that this is actually a medium repair. Sort of like when you go into Starbucks and you want a grande, but you realize there's something bigger out there. And this is the venti. So when we started the venti on the job, we decided I needed to change a plan. I wasn't satisfied with just another Shotcrete repair. And what do all good engineers do these days? You go to Google and you see what's available for other people trying out this business. So the end of the result is the photo on the right. We did a box style repair, and I'll explain a little bit of that background. When we went to search for suitable repairs, we did find that Michigan had researched this in 1999. There was a report produced in 2000. And what they did, they had a FHWA person and a Michigan DOT rep draft up a repair procedure, and he said, well, let's try this. And they brought this salvaged pre-stressed beam into the lab, and they chipped away to create some artificial damage, to my understanding, and they severed a stirrup and exposed some strand, and then patched it. And then they patched it with this big end block, and then they loaded it. And their conclusion was up to 1 stirrup and 12 inches of strand may be exposed without pre-stress or shear strength loss. And I say to Michigan, really, 1 stirrup? You're in a lab, you can go a little further. So we had damage beyond Michigan's experiment. And we started to look at our issue, and we couldn't think of a better repair, and so we progressed forward. You can see on the right, we did anchor through the beam after locating the internal reinforcement and pre-stress. We designed it as a conventional mildly reinforced repair, just with the original beam strength. And we also noted that Michigan suggested this jack out there to relieve the pressure. And that made sense to us, right? You want to get the load into this block and not have it go through that old deteriorated concrete. So when we got out there, we did the same thing. And it was a Saturday morning, and I received the call from an inspector saying, Paul, it's starting to breathe. And I didn't really know what that meant, and so what do you mean? And he says, well, the web is starting to split. And I said, oh, quick, let's take off 50% of that dead load pressure and get those pre-stress forces back into balance. And it turned out that my theory is the pre-stress was ripping that beam web apart and trying to redistribute. So we restored some of that bearing pressure and got it stabilized and progressed with the repair. So this next series of slides is the sequence of the repair. You can see metalizing on the face of that beam. They didn't coordinate the subcontractors very well, and so the thermal zinc spray came on first, and they hadn't even done the repair yet, so we had some communication issues with that contractor. So here's the process, the sandblasting. Chipping out any loose concrete. Now, we told him to stop at the web. I think he could have punched through fairly easily had he wanted. Had a lot of strand exposure, many severed ones. And it was October. We had some cooler temperatures, and we needed to heat and house. It went out about 4 feet from the beam end. And we were in a swamp, so we kind of had a jack and hold curve until we reached good compaction underneath there for that temporary support. We chose Shotcrete as a repair material because it's really the best at getting in between all those tight spaces and getting some bond. When we've tried grouting or just a form and pour, it hasn't always resulted in the best bond against those surfaces, especially for overhead or vertical. Here they're shaping the Shotcrete and finishing off the underside. And this is the end product. Now, we had a lot of other issues with that repair contract. In fact, we noticed underneath they had scuppers wherever there was an expansion joint, and this was every other pier for 49 spans. So all that salts and water was leaking onto an old roadbed, and we started to find some deteriorated piles. And so you start to notice one, and lo and behold, its neighbor doesn't look too good, and lo and behold, the other one has some losses too. And so we also, by supplemental agreement, had some mild reinforced repairs in there. And I just say this because I think a lot of you might have these conditions where you have moisture that isn't draining well underneath your bridges, and you should be aware if you got pre-stressed beams in those conditions, or pre-stressed piles. And we ended up with our tree forest underneath there. So there's a lot of questions about durability, and this job was definitely a lot of questions on how long this thing's going to last. And when asked by the district, when should we program this for replacement, I said, well, I give it 5 to 7 years, which is your normal expectation for shotcrete in chlorides. But when you think about this bridge and when we replace it, we usually like to put all the traffic on one bridge and give it its worst loading of its life at the end of its useful life. I said, so you really want to do that? And they decided probably not. So we went out there quite a bit and monitored cracks and crack growth on those repairs. And until it was replaced in 2017, we had 3 years in service, and we had found out from that same contractor they had done similar repairs in Wisconsin, as well as Tennessee for the U.S. Army Corps of Engineers. But we don't know of any real testing on that repair, and so I sought some research money when I found out this bridge was being replaced, and we were awarded that money to test in a lab. The testing was fairly simple. You're going to salvage 2 of those beams that were repaired in that manner with the box end repair, and 2 beams that were in good condition and bring them into a lab and test all 4. Did we restore to the original design strength? Nothing complicated about what was the exact section loss in there to develop formulas. So the hurdles we had, the U of M laboratory could only fit a 38-foot girder. We had 60-foot long. The bridge contractor was very on board, so we needed an SA to salvage that. And the U of M could only lift so much weight into their lab. And so we had to cut it down to size and take the deck off. And so this is our salvaged girder. And we left the deck on over that repair because we didn't want to impact damage the shotcrete. But elsewhere, we had to remove the deck for weight purposes and saw cut it. And then we brought it into the lab and had to cast a narrow deck, a 10,000 PSI deck, back on this girder to try to simulate an original deck and get a shear failure to occur. Otherwise, it wouldn't have been the failure we're looking for. So we brought it in there, and the load point was about 13'3" from the end on a 38-foot long girder. We needed to be 2.5 times the depth of the beam away from the end to ensure a shear failure. And at the other end, where it was saw cut and you had wider shear stirrup spacing, we put external confinement so that it wouldn't fail there. The testing started out at 50,000 pounds initially, and then we ran displacement control and loaded it in 25,000 pound increments, and we'd hold and map the cracks. So this is the test, and I got to my left the original shotcreter from the job. Failure load, we had applied 465,000. You can notice that the shear failure actually went outside of the repair. Now here's a normal beam, and the shear failure kind of trajectory had been a little more towards the support. Now I had a lot of questions going into this. It's the original beam in 2013 prior to repair. A lot of hollowness underneath. So things normally don't look as bad as when you start chipping. And like I said, I had a lot of questions on shotcrete. Is it going to bond well? Is it going to hold on there? Or just separate like a clam because you're incrementally loading this thing? And when they applied this, I noticed that they didn't take off all the cathodic protection. So we had some potential debonders for this shotcrete. Again, this was the second one with a normal beam next to it. So by all intents and purposes, we did restore the original strength of the beam. The load failure did occur outside of the end. I didn't find any debonding of that shotcrete. There were some shrinkage cracks in the end block that were there from 20 days out, but they didn't grow really over time, very minimal. Good bonding against the web, even with that thermal spray against the concrete. And a lot of these cracks that you see marked in the end block were there from the get-go. So here's just a summary. We did receive our first flexural crack at 300 kips versus 275 for this pair. So very similar behavior between the repaired and unrepaired girder. The load displacement curve is also very similar. And I'm not going to spend too much time on this slide, but AASHTO would have projected a nominal capacity of 204 kips, and we actually achieved about 30% more than that. And that was just using the beam original strength. So repair costs, our normal shotcrete repair on that job we were running about 755 a beam end for those small type repairs. And when we did this SA in 2013 for 2 locations for the box repair, it was $5,500. And then in 2016, we had another instance on another contract. It was $12,500, but that was kind of up there in hard access. And then in 2017, we actually bid it out as a repair with a quantity of 5, and they were $10,000 each. Shoring was extra in that job. Now, we learned a lot of lessons from that. We don't think you need the shoring to do the repair, depending on the level of severity. And we think it's a very successful repair. It employs repairs that you would be doing elsewhere on the job had you had a substructure repair. It's not like bringing in an FRP crew, a subcontractor to follow up. So many thanks are due Research Services for funding this, Ames Construction for doing a good job on salvaging the beams, and our Eden Prairie Maintenance Bridge crew potholed about 100 piles out there to help me assess those things and longevity. And then our inspector was really good at getting all those photos for me. If you want to see the full text of this, it is available on our website. Now it's published as of March, and there's the link. I think this presentation will be posted so you can pull it from there.
Were you able to keep traffic on the bridge at all times, especially during when the cracks were starting to propagate?
After it was repaired, we had no interruption of service. During the repair, I had wanted an interruption of service so that we wouldn't have those impact forces, but it was deemed that we could not do it with that route. It was just too busy. We had 2 lanes and narrow shoulders, and so we held the jack there and we did the repairs under live load. So I think it gives a real illustration of authenticity to this repair. And we had it in service for 3 years, so it performed very well.
Severe corrosion. One quick question I had for you is, were you able to determine how far out from the end that you had corrosion issues, section loss issues, what kind of section loss you saw, and
what kind of section loss did we see? I do have in the report the exact strand losses, and the stirrup losses. You know, you use a thumb and you're doing your best because it's all where the weakest link is in the stirrup itself. And so I think that is somewhere where we are lacking is how much section loss, spalls concrete at different cover depths and strengths of concrete, and I did my best to estimate it, but I'd think about 3 feet from the end.
I was a little surprised to see the amount of damage that you had on beam ends and on the piles that you had at ground level. Do you have any comments on corrosion-related damage to the bent caps? Because I really didn't see any of that in your presentation.
We had quite a bit. Now these were close spacing piles. In fact, that first picture in this presentation, we went all the way to the pile. But they were almost every beam, there was 1 or 1.5 piles. So the pile cap itself was not necessarily distributing a lot. The piled bents, yes, we had extensive corrosion and spalling of those. Definitely some worse than others.
Yeah, I guess, so I understand the end of the beam, you were saying that you were concerned that he could actually put his hand through the web or continued knocking off the deteriorating concrete.
We didn't want to chip further because we knew we were going to encase this thing. So what was the point of punching through it? And it was intact and holding at least the pre-stress balance at the time.
So was the design, in essence, the consideration that all you had to do was basically encapsulate the end and transfer the shear from the deck, but not worry about the strands and they're pulling through the deteriorated concrete that's there?
The design was very crude. I think it's about 1.5 pages of calcs of a mildly reinforced block of concrete with 5,000 PSI in that stirrup. We didn't try to figure out the composite section, so to speak. And I didn't do the design, so I can't speak to it, but elsewhere, you know, we tried to take a simple approach and just treat it like a mildly reinforced block and a beam.
So the attachment between that block and the original pre-stress, you weren't concerned about the connectivity of the strands transferring that load through this new block?
We wanted to get outside the area of corrosion, definitely. And so we set a distance of 4 feet, which was beyond the 3 feet where we started to see corrosion. But yeah, I don't think they ran a development length. I think they just said, let's get a nice block there. And looking at the test results, it seems like the rigidity of that end almost forced the more flexible section outside there to fail. Now the stirrups were spaced further out there, so maybe I have had some criticism, well, you didn't test a damaged beam, but there's no way we're leaving a damaged beam out there when we can do a repair for $5,000 and not worry about it. So I think it's money well spent. Well, thanks a lot, guys. I do have a YouTube video out there of this if you want to look for it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.